Today I'm going to talk about how to use micromotors to enable the modulation of biomolecule absorption and desorption rate for various biomedical applications. If you are familiar with these two devices, on the left is the rapid test kit of the COVID-19, which is also a lateral flow immunoassay, which can detect the COVID antibody when it binds to the sensing site on the device, which requires the absorption process. And on the right is the lipid particle drug carrier, which carries the mRNA, the vaccines, and release into human body at a moderate release rate. So for both systems, either for sensing or drug delivery, they both require a mass transfer process in the opposite direction. For the sensing, a fast reaction rate is always more absorption rate is always preferred, so that you can get the result in a shorter time. But for the drug delivery, sometimes you don't want the release to be too fast or too slow. It has to be in a moderate or even a tunable manner for the desorption rate during the release process. And like both systems has a lot of similarity in between, the same underlying physics, and it's important to develop the universal approach that can tune either the absorption or desorption rate over a wide range based on the same working principle, so that it can be applied for a wide range of applications. Here shows the general picture of the absorption-desorption system. Involves convection, diffusion, and reaction. For example, a sensor usually have a low concentration of analyte near the surface and high concentration in box solution. And for the drug carrier, the concentration of an effective component is high near the surface and low in box solution at the very beginning. And they all involves a diffusion regime and a convection regime and the external box solution regime. So in most systems, the diffusion step is a rate limiting step of the entire process. We will demonstrate that in the next few slides. And we developed a new type of a micromotor, which is made of silicon oxide diatom and functionalized with a bilayer of gold and nickel on the surface, so that it is responsive to the magnetic field. We also functionalize the surface with silver nanoparticles so that it can work as a sensor to a lot of kinds of biomolecules when shined by the laser. And here shows our experimental setup. We have a magnetic stirrer to generate a rotating field, which can actuate the rotation of our micromotors in a microfluidic PDMS chamber. And we shine 532 green laser from the bottom to the surface of our micromotor, which can excite the surface enhance the Raman spectroscopy of the certain biomolecule. And we use DNA as a testing example system, which has a 2000 base pair and with only a very low concentration of 80 nanomole in the system. And we figured out that at different rotation speed, the absorption rate of the DNA molecule to our microsensor has dramatically changed. When we increase the speed from 0 to 1200 RPM, the absorption time, characteristic time, decreased from 500 seconds to about 100 seconds, which drops about 4 times. And there is a power law between the time of absorption to the rotation speed of minus 0.4. So we conducted the numerical simulation, trying to understand why a higher rotation speed can result in a shorter absorption time. And here shows our model with constant flow rate carrying the same concentration of analytes, and at sensor surface the concentration is 0. When there's a different flow rate, which is corresponding to different rotation speed of the micromotor, the concentration profile changes a lot, and which affected the diffusion process dramatically. And by doing the scale analysis, we figure out that when the rotation speed or the flow rate increased from 10 to the minus 5 meter per second to 10 to the minus 3, the diffusion layer thickness decreased from 6 micrometer to 1 micrometer. And there's a parallel between the diffusion layer thickness to the rotation speed of the micromotor. And a thinner diffusion layer will result in faster diffusion process, which accelerate the entire absorption process. And overall, we demonstrate how to use micromotor to tune the absorption and desorption rate simply by varying its rotation speed. And on the right shows the video of a rotating micromotor assembled into our fluid PDMS channel. And we also conducted numerical simulation and scale analysis and understand why a higher rotation speed result in a decrease of the thickness of diffusion layer and causing the acceleration of sensing and release process. And eventually we try to use this technology to address the challenge for biosensing that with both high sensitivity and high speed, which is almost impossible in the past. And we are also aiming to achieve precise tunable drug release based on this tunable rotation speed of the micromotor for more precise drug delivery. Thank you.